Thank you everyone to join this open source firmware conference. I'm Jiewen Yao, Principal Engineer in Intel. Xiao Yuran is my colleague. He is also Principal Engineer in Intel. Today, we will introduce OpenSPDM, an open source SPDM implementation for secure device communication. To introduce myself, I'm Jiewen Yao. I'm being engaged as a firmware developer for over 15 years. My focus is firmware security, and I'm a package maintainer in open source UEFI firmware EDK2. And I create the open source Open SPDM project since last year. Xiao Yuran has over 16 years of experience in cryptography and security architect and implementation on embedded systems. He is the co-author of the DMTF SPDM specification. First, let's have a brief introduction for the SPDM. SPDM stands for Secure Protocol and Data Model. It is a specification defined by the DMTF and PMCI working group. SPDM's vision is to resolve the long-lasting problem of a compatible secure communication solution between two endpoints of the embedded systems. To the end, SPDM defines the message formats, data objects, and the sequences for performing the message exchanges. The protocols defined by SPDM can be used for a wide range of secure functionalities, such as authentication of the hardware firmware identity, delivering measurement, and performing the attestation. Also, the secure key establishment used in a session. In December 2019, SPDM 1.0 specification was released. It described how to authenticate the device and collect the device firmware measurement. In July 2020, the DMTF released the SPDM 1.1 specification, which adds the device session establishment for the secure communication, which is similar to a network TLS protocol. Currently, DMTF is working on a future version of SPDM specification. The SPDM is adopted by multiple organizations besides DMTF. There are PCI in CXL or MIPI, USB, TCG standard body are referring to SPDM. This figure shows SPDM 1.0. The left-hand side is a SPDM requester. It sends a SPDM request message and receives the SPDM response message. The right-hand side is a SPDM responder. It receives the SPDM request from a SPDM requester. Then it sends the SPDM response message to the requester. In order to create a connection between the SPDM requester and the responder, the requester needs to send a get version, get capability, and negotiate algorithms. These three steps are the foundation of this communication. Then the SPDM requester can get the device identity of the SPDM responder device by using get digest or get certificate. Once this message is received, the device will send back the device an X-file9 certificate chain or the digest of the certificate chain. Then the SPDM requester can use a challenge command to authenticate the device. Then the device must assign the nonce in a challenge message with its own private key and send the challenge auth back. The signing algorithm could be RSA, SSA, and RSA PSS or ECDSA, which is negotiated in the negotiate algorithm command. The certificate chain just shows the identity of the device, but it cannot tell which version of the device firmware is. In order to know more detail of the current device state, the SPDM requester can use get measurement command. Once that command is received, the device can return the measurement of its immutable root of trust, immutable firmware, as well as the configurations. The device must send this measurement response message back to the requester with a nonce to resist the replay attack. SPDM 1.1 introduced the session concept. SPDM requester and responder can create a secure session for uh, a secure session with confidentiality and integrity support. There are two possible ways for a secure session. The standard ephemeral Diffie-Hellman key exchange plus authentication, or with a pre-shared key. When the ephemeral DH key exchange algorithm is used, it could be finite field DHE or EC DHE, and both sides will negotiate a ephemeral master DHE secret. Then the two entities use the key schema algorithm to derive the data secret key and encryption key and the initialization vector for both request direction and the response direction. Once that data is get, then the requester and the responder can use the standard authenticated encryption with associated data and AEAD algorithm for the communication. The AEAD algorithm could be AES, GCM, or Cha-Cha Poly, which is negotiated in the negotiate algorithm command. If the key exchange is used, then the authentication is required to resist the man-in-the-middle attack. Similar to TLS, the SPDM sessions support one-way authentication or mutual authentication. In handshake phase, the SPDM responder always needs to sign the handshake message with its private key. If the mutual authentication is used, the requester also needs to sign the handshake message with its private key. This is the first way to create a session. The second way to create a session is use a pre-shared key, also known as PSK. When the PSK is used, then the requester and the responder can establish the session with a symmetric key cryptograph. This option is especially useful for the endpoints that do not support asymmetric key cryptograph or certificate processing. Essentially, the PSK served as a mutual authentication credential. It is also the base of the session key establishment to derive the data secret, encryption key, and the IV. SPDM specification declare the message data object and the sequence of performing message exchange between devices. SPDM spec does not define how to transport the message over different media. The transport layer of SPDM is defined by other specification. For example, SPDM can be over DMTF and CTP message, which is transmitted between the SM bus devices. The PCI-SIG defines the PCI data object exchange standard, known as DOE. The SPDM message can be transmitted via the PCI DOE mailbox. The USB organization also defined the USB control transfer for exchanging the SPDM message for USB devices. SPDM is also adopted by other standard organizations. For example, the TCG platform firmware profile specification adds the device firmware measurement. The device hardware firmware code can be extended to PCR2 with SPDM firmware block event tag. And the device hardware firmware configuration can be extended to PCR3 with SPDM firmware config event log. In part 1, we introduced the SPDM specification, and in part 2, we will introduce the OpenSPDM. OpenSPDM is an open source tool to validate the SPDM implementation. It is BSD license. It is written in C language. OpenSPDM includes an SPDM requester utility to validate a vendor's responder implementation. It also includes a SPDM responder utility to validate the vendor's requester implementation. This SPDM utility can be built in a different execution environment. For example, it can link with the standard C library and run in the OS environment. It can dump the SPDM execution log, and the developer can trace the SPDM execution flow. Currently, we have submitted the OpenSPDM tool to DMTF organization as a validation tool, so it can help to validate the SPDM implementation. This picture shows the OpenSPDM design. It is the architecture of the OpenSPDM tool. In the middle, you can see there are some green boxes. There are SPDM request lib, SPDM common lib, and SPDM responder lib. Those three libraries comply to DMTF 274 SPDM specification. The SPDM request lib provides the services for the SPDM requester. For example, it has API to send get version, get capability, or negotiate algorithm to the responder. It can also start session or send the application data for the session. SPDM responder lib provides services for SPDM responder. For example, it has a callback function to process the SPDM request message and build the SPDM response message. In the middle, you can see SPDM common lib is to provide the common services for both requester and the responder. For example, the key schedule algorithms for SPDM session. Since SPDM 1.1 introduced the secure session, the SPDM message is encrypted by the AEAD algorithm in a session. The SPDM secured message lib is used to encrypt or decrypt a SPDM message in a session. This is following the DSP 277 secure message using SPDM specification. The blue box is the transport layer library. The transport layer bounding is not defined in SPDM, so we only provide the default MCTP bounding. The SPDM transport MCTP lib is used to encode the SPDM message into a MCTP message in SPDM requester. And it also decodes the SPDM message from a MCTP message into a SPDM response message. The gray box is a device I/O. The OpenSPDM does not include any hardware device I/O such as SMBus, PCI DOE, or USB control transfer libraries. The SPDM consumer need to implement this device I/O library API and register to OpenSPDM to send or receive a SPDM message. And in the bottom, it is a crypto library. OpenSPDM itself does not implement any crypto functions. It defines a set of crypto APIs such as hash, HMAC, asymmetric crypto, AEAD, or random number. The SPDM consumer may link other crypto library to support those crypto API. In reference code, we provide two examples, OpenSSL library and Embed TLS library, to show how to implement the crypto APIs. A device may also use the hardware crypto accelerator to implement those crypto APIs. In summary, the OpenSPDM implements the command defined in SPDM 1.0 and 1.1, including the device authentication, device measurement, and secure session. It supports the third-party crypto engine binding, such as OpenSSL or Embed TLS or any hardware accelerator. It defines a crypto API for SHA-2, SHA-3, and RSA, SSA, RSA PSS, ECDSA. Finite field DHE, ECDHE, AES, GCM, or Cha-Cha poly algorithms. The OpenSPDM library uses a context buffer to store the communication parameter between two entities. The OpenSPDM library does not need a heap, and it does not use any global variable, which is essential for small devices. But the heap or global variable may be used in OpenSPDM consumer based upon the consumer's execution environment. Currently, we can link the OpenSPDM as an OS application and test it the OpenSPDM requester or responder. For example, in UEFI environment, we can link the OpenSPDM as a UEFI SPDM requester driver to authenticate a device or collect the device measurement from it. In BMC environment, we can link it as a SPDM module as well to communicate with other devices. The OpenSPDM can build with Windows Visual Studio or Linux GCC or LLVM CLAN compiler. However, the OpenSPDM is not a complete solution. Even if the OpenSPDM is used, there are some additional work need to be done by the device vendor. For example, the OpenSPDM does not include crypto services, especially for the private key or the random number generation. The vendor must implement a crypto library to sign the data or maybe a hardware accelerator. The vendor must implement how to protect the private key. The vendor must implement a random number generation. And thus, the device vendor should put the SPDM to a protected execution environment to prevent local attack or side channel attack, especially for the key leakage. The vendor must provide the transport layer send and receive, such as MCTP or PCI DOE. The vendor must implement the proxy to extend the measurement to proper TPM PCR to support the TPM-based remote attestation. The vendor may implement the use case to use SPDM session, such as PCI key programming for a link encryption setup. There are a lot of things not existing in OpenSPDM. We want to leave it to a solution builder, but not here. The value of OpenSPDM is not to replace the vendor's implementation, but it can help to validate the SPDM implementation, see if it works, because most vendors may just implement partial, either requester or responder. For example, if you are a PCR card vendor, you want to implement the SPDM responder, then you can use OpenSPDM as a requester to validate the responder's implementation. For example, if you're working on SPDM device authentication or measurement attestation, you can then you probably implement SPDM requester. Then you should use OpenSPDM as a responder to validate the requester's implementation. And here is a size result when we build a OpenSPDM library. The raw library without crypto services about 20 kilobyte, but if we link embed TIS, the library is more than 100 kilobyte. For the rest, we will show some demo to see how OpenSPDM works. Here is a message dump from the OpenSPDM. They are running in the OS environment. The left-hand side is the SPDM requester, and the right-hand side is the SPDM responder. This should the get version request. On the right-hand side should the version response. You can see the last 4 bytes 0010 means version 1.0, and the 0011 means version 1.1. This demo shows how the challenge or challenge OS works. The right-hand side shows the SPDM responder is calculating our M1, M2 hash, which will be signed by the responder's private key. The left-hand side shows the requester verifies the M1, M2 hash signature and shows the signature pass. And this figure shows the session creation for the requester and the responder. The left-hand side shows the SPDM requester generates the client random number and the client Diffie-Hellman key and send to the key exchange request. And the right-hand side shows the SPDM responder generates the final session encryption key and IV and send the key exchange response back. And this demo shows the secured message in the SPDM session. Both sides use a DMTF and MCTP message, and the message is encrypted and masked with AEAD algorithms. In summary, we introduced the SPDM specification. It is well adopted in multiple standard organizations. SPDM can be used to authenticate the device and collect the device measurement. And the SPDM session can be used for secure communication between devices. Then we introduced the Open SPDM. It is an open source tool to validate the SPDM implementation. It is BSD licensed and it's written in C. It helps you learn SPDM and create SPDM capable devices. Here is some reference we want to list. The fundamental thing is the SPDM specification. You can get it from the DMTF PMCI working group. The nice thing is that the PMCI working group created a white paper, DSP 2058, to introduce background on some information about the SPDM, including the threat model, certificate, attestation, and the security policy, etc. We also list some other standards related to SPDM. And here is a link of the Open SPDM. It is a temporary location. It is still under heavy development, and we submit it to DMTF as a tool for SPDM. And the second link shows how we use the Open SPDM in an EDK2 environment to create some code for the device security. That is all my presentation today, and we'll pause here to see if there are any questions for today's talk.